Hello, everyone. I'm Daniel Liang. In this video, we will begin to introduce developing efficient algorithms in chapter 16. We're going to introduce to use the big O notation to measure the time complexity of a program. In the data structures class, we use data structures to create efficient algorithms for processing data. How do you measure the efficiency of an algorithm? Well, you may simply say, I'm going to implement the program and run the program on the computer and get the execution time. But there are a couple of problems. The first problem is the running time of your program is really dependent on your system load and also on your computer. So if you have a very powerful computer, and you may get faster execution. If you have a slow computer, and it takes a while. And also, even you compare running two programs on the same computer, it depends on the system load. If you're running a lot of things on the background, then your system is slow. So that's one problem. And just running the program is not a good measure and for predicting the algorithm efficiency. And the second problem, it also depends on the specific input. Sometimes if you have a data in certain order, if you sort it, and you may get a fast execution time. And if in a different kind of order, you may take a long time to get the result. So that is all depending on the computer and the specific input. So now what we are going to look at is in theoretical term. So we're going to measure the complexity regardless of your computers. And regardless of any specific input. So we are going to measure the algorithm in the worst case. In theory, and we look at the algorithm and how the execution time will grow with the input size grow. So we're going to look at the growth rate, and the growth rate, it's going to give us the good indication and how the algorithm behaves. So the algorithm complexity is to look at the growth rate of your algorithm. And when the input size grows, and what about the time changes? So we're going to use the big O notation. So let's first look at the linear search. The linear search algorithm compares a key with all the elements in a list. In the worst case, if the key is not in the list, and you're going to spend n times to compare. And suppose the list size is n. So that's the n size. Now, if the key is in the list, you're going to spend average, it's half of the list size time to compare. So if you have the size is n, it's n divided by 2. That's the average time. Now we're going to look at this the list, if we double the size of the list, and your time is going to be doubled. So that's the growth rate, and growth rate is linear growth rate. So in theory, in computer science theory, we use the big O notation, and this is the big O notation, and to abbreviate for the order of magnitude. So using this big O notation, we're going to write the complexity of linear search as order of n. So this is the pronunciation, it's order of n, and using this big O notation. So essentially, the big O notation is to look at the growth rate. So this is the linear growth rate. When you double the size of the input, and the time is going to be doubled. Now, let's look at this, the best and worst and average case. And we're going to most interested in the worst case. So what is the first, what's the best case? The best case is you have the input that results in the best time. So that's the best case input. And the worst is you have the input that results in the worst time, takes the longest time. So that's the worst case. And the average case is you consider all kinds of input and get the average. So that's the average case. Now we know the best case is not representative, and the worst is not either. But worst is better than the best. So you can always say in the worst case, this is what. Okay. So that's, it's not going to be even worse than this. So that's worst case is give you the measure, and that will predict the behavior of the algorithm in the worst case. And the average case is very difficult to achieve. And for most algorithms, it's very difficult to get all the cases, and very difficult to analyze all the cases. So we are going to focus on the worst case in the most of the our algorithm analysis, unless we can easily get the average case. Now, the big O notation, you can really simplify it. So let's look at how you can simplify it. You can ignore multiplicative constants. So let's say we have the order of n, and order of n divided by 2, and order of 100 times n. So all of this, it's the same as order of n. Because remember that we focus on the growth rate. The growth rate is the same, whether it's n divided by 2 or 100n. This can be illustrated from this table. So we have n is 100, and this is the n is 100, and if n is 200, this is 200. See, the ratio is 2. So for this function, and this is the growth rate here, that if you double the size, and so you see the time is going to be doubled. So this is the growth ratio. And if n divided by 2, so this is n is 100, it's 50, and this n divided by 2 for n is 200 is 100, and 100 divided by 50 it's the same, it's 2. So all this is 2. So growth rate is the same. And for this reason, so we are going to ignore the constant factor. So this ignoring multiplicative constants. And you can also ignore non-dominating terms. So let's say we have this complexity, it's order of n, and here's order of n minus 1. So this item minus 1, this can be ignored, because we're going to look at the input n is going to infinity. It's huge, extremely large. So as n grows to infinity, and you only need to focus on the dominating part. So dominating part for this case is n. So if you have n minus 1, so that's n. So order of n minus 1 is the same as order of n. So we're gonna all ignore the non-dominating part, the smaller parts, and only focus on the large part of the expression. So this is common mathematical summations we use in the algorithm analysis. So this is summation of all the numbers, 1 plus 2 plus 3 plus n. So that's the result, and this one here. And so for this is 1 as 2, and so all this add together, and that is this. And this is the one here is 2 is 0, 2 is 1, 2 is 2, 2 is 3. So add this together. This is the common mathematical summation we used in the algorithm analysis to get the time. That is all for this section. We will continue in the next section and see you on the next video.